All right, well, I know that the square root of x minus 3 is nothing more than a transformation horizontally 3. So, I'm going to take this point, I'm going to move it over 3. I'm going to take this point, I'm going to move it over 3. And then I'm going to take this point, which is the point 2, 4, and I'm going to move it over 3. So then I'm going to end up at 5, 4. So 1, 2, 3, 4. Wait. This is 4, 2. I'm sorry. 4, 2. So I should end up at 7. So 1, 2, 3, 4. Okay, anyway, so our new graph kind of looks like this. So this is the square root of x minus 3. This is what it looks like. It looks the same as this graph. It's just shifted over 3. So this is a really important idea when it comes to graphing functions. It's the idea of if I have any given parent function, if I know what the parent function looks like, then I can take the parent function and I can shift it over horizontally, vertically, or I could scale it. I could apply the transformations to find out what the new graph looks like. So that's very, very important, something that you should think about maybe in your free time. Maybe have friends over and you can discuss this. I don't know, or I don't know. Maybe you'll have homework with it or something. Wouldn't that be great? But now there's more I could do with this. So if this is what I'm defining f of x to be. I'm defining it to be the shifted parent function horizontally 3. Now I could apply more transformations to this. I could apply again, maybe a scaling. Maybe I want to apply scaling of minus 2 f of x equals minus 2 square root of x minus 3. Well, okay, then I'm going to start out with this f of x, and I'm gonna do my scaling. So 0, 0, it's still going to go through that point because the y value, again, the scaling is just multiplying y values by the scaling factor. So here the y value is 0, so it doesn't matter because 0 times negative 2 is still 0. And then if I want to multiply this is the point. I guess this is 4, 1, but the y value here is 1. So after applying the scaling factor of minus 2, the y value should be minus 2. So it's like here. And then here, the y value, well, okay, your y value is 1, so it goes to minus 2. Your y value is 2, so it should go to minus 4, which is going to be like farther down here. And then maybe just for fun, or not just for fun, have some kind of distinction. I'll say that this one can be in the pen. Again, I wish I'd colored pencils, but some distinction is better than no distinction. And I get something that looks like this. So I know that this graph, the minus 2 scaling factor, it's going to have that effect. It's going to flip it across the x-axis because of the minus sign, and it's also going to stretch it out by a factor of 2 in the vertical. And then the last thing that I can do that we've been building up to, I say building up to, but it's not actually any harder. Arguably, it's easier. What if I had apply one more transformation? So I'm going to start with. I'll do this in the pen. It's a little marker. It's a little easier to see. What if I had the 2 times f of x? Then what if I added like plus 3? Okay, well that's going to be minus 2 square root of x minus 3 plus 3. Minus 2 square root of x minus 3 plus 3. You might have looked at that before today and been like, okay, well I don't really know how to graph it. There's a lot going on there. Or maybe you did know how to graph it. I don't want to insult or underestimate anybody here. I don't really know. But the point is now you definitely do. So I have this square root of x minus 3. I applied one transformation. It may go like this, which is really 2 transformations on the original square root of x graph. Let's not be confused by that. And then I want to shift it up 3 now, because that's all this is doing. Is if I add a constant multiple outside, it's just going to shift it up. So that means all I'm doing is I'm adding 3 to every y value. So the scaling factor that multiplies the y values by the scaling factor. Now here, this outside addition, it's going to add this shift factor. I don't know what the technical term is, but we're adding this number to every y value. So here the y value is 0, and I'm gonna transform again from this function. We're gonna start here, and then we're gonna transform. So we started with square root of x, shifted it, scaled it, and now I'm gonna shift it up again. So this y value is 0, so the new y value is gonna be 3. This y value is negative 2, so the new y value is gonna be 1, so it's gonna go through this point. And I'm using a pencil this time. And then this y value is -4, so when it's going to end up being a -1. Okay, and then I have those 3 same points, so I'm just going to go ahead and kind of sketch what I think the curve's going to look like. This new curve is going to go something like this. Okay, so again, I'm just going to take a moment to appreciate, label all my cute little plots here. This one, ooh, if I wanted to, I could be like, keep it dashed. Oh my gosh, aren't I a genius? Square root of x, get it? Because it's dashed. Isn't that funny? Anyway, that's square root of x. And then this one is the square root of x minus 3, because I shifted it to the right 3. And then this one in the pen is -2 times the square root of x minus 3, because I applied that transformation. And then in the pencil here is -2 times the square root of x minus 3 plus 3. And then, yeah, okay. So now you know how to graph functions. And again, I'm going to repeat myself. The only real idea I'm using here is if I know what a parent function looks like, then I can apply transformations to a parent function to get the graph of any new, more specific function. So it's essentially the only real thing you need to know going into this is what the parent functions look like. And again, even if you don't know what they look like, you can kind of figure it out by plotting points, thinking about it, maybe rubbing your chin a few times or eyebrow raising, I don't know. But so yeah, I mean, you should be able to figure out, but good ones to know like off the top of your head, like I know what this parent function looks like. Obviously, you should know what f of x equals x looks like for the parent function for linear graphs. Like you should know what that looks like. Okay. Additionally, it would be smart for you to be aware of what the graph of f of x equals x squared looks like. That's the parent function for a parabola. Of course, it's just, our U shape. But yeah, you should be familiar with how to plot that quickly. I know it goes to 0, 0, 1, 1, 2, 4. Anyway, yeah, so you should know what that parent function looks like. Other parent functions, I don't know. It's up to you how far you want to go with this. I mean, you'll cover a number of other different types of functions. I mean, you could keep going up the line with polynomials if you want to know like x cubed. It just kind of looks like this. But again, you may or may not be familiar with that. Again, there's like f of x equals 1 over x. It's not a bad idea to have like what these graphs look like in your head. There's the exponential of x, e to the x. Hopefully I'm not like saying random functions that you haven't dealt with yourself or you don't remember what they look like. Because if you don't, like that's okay, we'll cover it. But it's just a good idea to, if doing well will be easier if you have an appreciation for, these different types of parent functions, so you have an idea of what we're dealing with when we go into these things. So it's it's not a bad idea to think about different parent functions. Hopefully, I'm not just blabbering right now, but okay, I'm just gonna move on. Does anybody have any questions about transformations? Okay. All right. Well, I'll talk a little bit about function composition. How about? So there's this idea in math that we can take functions of functions. So it's like, and this kind of aligns with what I was saying before. If I plug anything into a graph, then I can replace everything by it. So if I have like two functions, f of x and g of x, okay, and then let's say let's say I don't know what g of x is. All right, let's say maybe I haven't defined that yet. It's not defined yet. And then but I do know that f of x is equal to 3x plus 2, obviously, right? Because I think I used that example already. Or maybe I didn't. I know right off the bat, before I even know what g of x is, I know what the composite function f of g of x, which sometimes they use this notation, which I think is kind of like stupid, but you should be kind of familiar with it, which is equivalent to f of g of x. I know that this composite function, it's going to take the form of 3 times g of x plus 2, because that's just by the laws of taking whatever is inside of f of x, and I'm going to replace x with that thing. That's the argument I made earlier today, and I'm making it again right now. Okay, So I know it's going to look like that. So then after I define g of x, then we can have a conversation about what this function looks like. If g of x is equal to x minus 3, then what do you know? The composite function f of g of x is just going to look like f of x, but it's shifted to the right 3. Then we go back into the topic of transformations. But instead of falling back into that sand pit, I think I'm going to move on and do something more interesting. What if I had like, how about this? So, okay, you guys get this idea. I'm going to move on. When I say move on, I mean not really move on. I just mean do something that is the same thing, but using slightly different functions, right? Because I realized my choice of functions isn't ideal for the point I want to get across. How about I'm going to say, but this was also a point in itself, the fact that, and it's a point I've already made before. The only purpose of this piece of paper was to reinstate the fact that I can plug in anything I want to into a function, even a function, and I get something out that looks like this. Okay. So that wasn't just that paper had a purpose. Anyway, so what if I had f of x equal 1 over x and g of x equal to 3x plus 2 example, okay? Then let's say if I wanted to take f of g of x, then this would just be 1 over g of x, like I said before, which is 1 over, now that g of x is defined, I can do 3x plus 2, something like that. And then here's something interesting we know. Here's a point that's worth considering, is the fact that I have created a new domain restriction by applying the composition of function rules. So before f of x has a single domain restriction at x equals 0, because I cannot divide 1 by 0. I can't divide any number by 0. Now in this case, the domain restriction, after applying this composition of functions, and note that g has no domain restrictions. But after applying this composition of functions, I get this new function that doesn't have the same domain restriction as f, because if I plug in 0, I get 1 over 2, which is totally kosher, that's fine. But if I have g of x equals, and I have g of x equals x plus 2, which has no domain restrictions, but this is not like g of x, and it's not like f of x, because it has some domain restriction, it's just not this one. And I know it has some domain restriction because it's rational function with a denominator that's capable of equaling 0. So now the question is, okay, well, I have this new composite function. What do I have to do to it to, extract the information that will tell me what the domain is? Where are the domain restrictions? Well, I know it's just going to be whenever 3x plus 2 is equal to 0, because then we have division by 0, which is true if and only if 3x equals minus 2, which is true if and only if x equals minus 2/3. So then we kind of know that through the composition of function, we have defined this new domain restriction. In this case, it's going to be kind of like an asymptote. But again, I don't want to. I might say words that haven't been defined yet, but that's okay, because if you don't know what it means, it's not going to hurt you, and it might make it less scary if you've heard it a few times before. Anyway, so yes, I have this new x equals minus 2/3. I know that this is a domain restriction of this, so that's an important thing to be careful with. The bottom line of this piece of paper is it's important to be careful when dealing with compositions of functions, because you will unlock new domain restrictions often, and it's good to be aware of what those are, because I don't know, maybe the question will ask it, maybe not. I don't know, but you should be prepared always. Okay, I think that's really all I'm going to say about transformations and composition of functions. So if you have some dying question about transformations or function composition, you can tell me that. Okay, looks like everybody is at peace with this topic. Okay, that's good to hear. I am going to spend the remaining 10 minutes discussing a new topic that you may or may not, be familiar with. Again, I keep saying may or may not be. You should be, in theory, if Adam is covering these topics, but I don't know. But even if you didn't understand it, that's okay, because I'm not going in depth here. I'm going to talk about even and odd functions. So even versus odd functions. Again, I'm using versus, but it's not really against each other. It's just more two different classifications of functions here. So I'm going to define these first before I start talking about them. A function is even if f of minus x is equal to f of x. And a function is odd if f of minus x is equal to minus f of x. Okay? So this is the definition. You can always check this using, check and see if a function is even or odd using these definitions. So for example, if I take the function x squared plus 1, f of x, I know that f of x is equal to x squared plus 1. I know that this function is going to be an even function because if I plug in f of minus x, I get minus x quantity squared plus 1, which is equal to x squared plus 1, which is equal to our original function f of x. So I get the same thing out whenever I replace x by minus x. It doesn't affect the function in any way. So we call it an even function. An example of an odd function, I mean, I don't know, maybe f of x equals 3x cubed minus x. So if I have f of minus x, in this case, with this definition of f, I get 3 times minus x cubed minus the quantity minus x, which is equal to, minus 1 cubed is minus 1, so I can pull the minus 1 outside of the cube. I get minus 3x cubed plus x, which is equal to minus the quantity 3x cubed minus x, which is equal to minus f of x. So that's if Adam on a test or something, or somebody else, maybe the textbook author, says, hey, prove that this function is even or prove that it's odd. All you do is you use the definition, you just plug in the minus x, and you show that f of minus x is equal to minus f of x, or f of minus x is equal to f of x, depending on if it's even or odd. Additionally, it's worth noting that a function doesn't have to be even or odd. There's no real reason why it has to be either of these properties have to be true. I just gave you 2 examples where at least one property was true in both cases, but there's no law that says that always has to be the case, right? That's just something that happens to be the case with some functions. Now, if it is the case, we do get some interesting things that happen that are worth talking about. So I'm gonna talk about them. Okay. All right. So let's consider. I'm gonna go back to my example of an even function. All right. My example of an even function was f of x equals x squared plus 1. Well, okay. Like I was saying before, we kind of know what that looks like because I know the parent function of a parabola is just the U shape, and then this is just the parent function of a parabola with the vertical transformation upward by 1. So I should know right off the bat that it's going to look something like this. X squared plus 1 is just y equals x squared. Everything's shifted up 1. So again, pretty much almost all function graphs. Like you want to know how to graph them. You want to be able to think about how to graph them just by, I know what the parent function is, and I see what the transformations are. I know how to apply those transformations, so I create a graph. Bing, bada, boom. Here it looks kind of pretty, right? But anyway, this is an even function. So let's recall even functions have the property f of minus x equals f of x. What that really means in practice, if we would talk about it from a graphical perspective, is that the negative x values are going to have the same y value as the positive x value. So if I consider f of negative 2 is going to be the same as f of 2 because I can replace x by anything I want to. So if I know this property is true, then I know I can take any specific x value and it will still be true. So if f of minus x equals f of x, then f of minus 2 is going to be equal to f of 2. Okay, well, which is, that's interesting, and we can check that. If I plug 2 into this function, f of 2, then I get 2 squared is 4 plus 1 is 5. F of minus 2, well, minus 2 squared is 4 plus 1 is 5. So yeah, I mean, this is definitely a true statement. And we've even verified it's true for all x before because I did that when I did this thing here. But besides the point, what it means in practice is that what it means is that we have symmetry about the y-axis, right? The y values on the right are going to be the same as the y values on the left. So it's like the same on both sides. This is what symmetry is, okay? So that's all you really need to know about even functions is this property is true for even functions, meaning that the y values on the right side of the y-axis are going to be the same as the y values on the left side of that y-axis, and that implies a symmetry about the y-axis. Now there are going to be some parabolas that you're going to encounter, or other functions, not just parabolas, but often parabolas. Maybe this parabola, I don't know. Now the thing is, parabolas always have symmetry. They always have symmetry about some axis. This parabola I drew has symmetry about whatever this axis is. Maybe it's the axis x equals 5. I don't know. It depends on how I'm scaling the x-axis. But the point is, parabolas are always going to have some level of symmetry about some axis. However, if the symmetry is not about the y-axis, then you're going to find that they're not even. Okay, this is not an even function, even though it is symmetrical. Even if a function is even, that implies that it is symmetrical. However, if a function is symmetrical about an axis, that does not imply that it's even. We require specifically that it's symmetrical about the y-axis for this to be true, and for this condition to be true, for it to be even. Okay. Now I'm giving even functions a lot of attention, so I don't want to be I don't want to be accused of being biased in favor of even functions as opposed to odd functions. So I know there's a lot of talk about people in the media being biased these days, and I don't want to be one of those people. So I'm going to do my time, and I'm going to consider this function that I had already considered. F of x equals 3x cubed minus x. This is the one that I proved was odd. I proved that it was odd because I replaced x by minus x, and then I applied these functions, and I showed that I got minus f of x out of it. Okay. If I wanted to graph this, I'm not going to talk about the exact specific mechanism for graphing this because that probably isn't obvious to you at this point, and I don't want to get tripped up on it right now because we'll talk about that at a later date. However, I kind of already know what it looks like because, I've taken this class before, I guess. The point is, I'm pretty sure what it's going to look like is something like this. Again, if that's not obvious to you, then, don't sweat it. Now, these odd functions, they don't have that same symmetry about the y-axis. Naturally, they don't. They have their own kind of symmetry, though. So for odd functions, we have this condition f of minus x equals minus f of x equals minus f of x. That kind of entails a symmetry not about the y-axis, but again, if you look at this and think about it, what kind of symmetry does that remind you of? Maybe that brings you back to days when you were a kid and you remembered that things were symmetrical about the origin here. But yeah, that's what it is. It's kind of if I flipped it about the y-axis and then about the x-axis again, I kind of have that going on there. And again, if that doesn't make like a ton of sense to you right now, that's like okay, but it's a good idea to think about things, even if they don't, fully compute. But again, it's kind of like I can't just apply one transform here. I can apply like one flip and I get that side. It's like convenient because it's like symmetrical there. Here we say it's symmetrical about the origin, and then it requires not just one but two flips. If I take everything on this side of the y-axis, I flip it this way across the y-axis, and then I also flip it about the x-axis. I kind of get this side back. It's like, you should be able to see what's going on here. So this is kind of a property of odd functions being symmetrical about the origin. They have their own kind of symmetry, separate from even functions. So we should know definitions of even and odd functions. We should know how to show that a function is even or odd. And we should have some level of appreciation for what that means graphically. There's like this green. Do you guys see that? Oh, it's gone now. Did somebody do that? Do you guys have permissions to do that? I saw like a green, like transparent line on the screen. That's weird. Oops. Yeah, I didn't. No, don't apologize, Craig. That's okay. I was just confused. I didn't realize that you had that power. Anyway. But I think I'm done talking for today. I've said a number of things about even and odd functions, function transformations, and scaling functions. So I mean, if you want to talk to me afterward, if I said something that bothered you, um, hopefully that's not the case. But let me know, or you can email me and we'll set up a meeting or something. By the way, you guys are good to go now if you choose to do such, or if you don't. I don't know. Maybe you don't want to leave, but you're busy. You have to go. Thanks.
Thank you.
No problem. All right, I'll see you all next week.
Thanks. See you next week.
See ya. All right.